Exercise 2239 is asking you to use the acetoacetic ester synthesis to make a few compounds, to make these methyl ketones. Now we came up with a recipe for the acetoacetic ester synthesis in the last video, and we explained what each of these different reagents is doing in this recipe. So let's write that recipe down for each of these exercises, and then we'll adjust it as we need for each individual molecule. In the recipe, what you always use in the acetoacetic ester synthesis is ethyl acetoacetate, and then you always treat that with sodium ethoxide in ethanol solvent, and then an alkyl halide that you have to figure out which one that's going to be. And you always end with aqueous acid, so hydronium, and heat. And we walk through what each of those things is doing and how it contributes to the overall change that you see in the molecule. The change happens to the alkyl halide. Onto that alkyl group, you add 2 carbons, carbonyl, and then a methyl group to the right of that. So that's what we're adding each time. So when we look at this molecule in A, we know that you always start with ethyl acetoacetate and sodium ethoxide. And to figure out what alkyl halide we have to use for this, we would just highlight the carbonyl and the carbons on each side. So highlight the carbonyl and the carbons on each side. Those are all going to be contributed by ethyl acetoacetate. And so they're not going to have to come from the alkyl halide. So to figure out what alkyl halide we want, we'll sort of erase those groups and replace them with a leaving group. Now it doesn't matter which leaving group you use, I'm going to use iodine here. And so that's the alkyl halide you want. That cyclohexane ring with the methyl group on the end, that's the R group that you would want. So I'll redraw that. Excuse me. And so that is your R group. So if you replace the R group in this recipe, this generalized recipe, with this specific R group here, then you can see that you would end up with the original molecule that we wanted, using that acetoacetic ester synthesis. Okay, so let's go through that same process for B. We know to use the acetoacetic ester synthesis, and even if they didn't give it to us in the instructions for the exercise, one of the signs that you could do that is that you have a methyl ketone. A ketone, carbon double bonded oxygen with a carbon on each side, with a methyl group on one side. That's a unique feature, and anytime you see a methyl ketone, you want to make a connection in your mind. I can make that from the acetoacetic ester synthesis. So what the acetoacetic ester synthesis does is it contributes this alpha carbon, carbonyl carbon, and then methyl carbon from ethyl acetoacetate. And so you see that feature in the final product. What you need to know is what the R group has to be in your alkyl halide to connect to that. All the rest of this recipe stays the same all the time. And what each step does is explained in that previous video. So highlight the carbonyl and both of the carbons on either side, and then erase all of those. So including that alpha carbon. When you erase that, what you'll notice is that you have 2 separated carbon chains. What that means is that we're going to have to do this step twice. We're going to have to put each of those carbon chains onto the alpha carbon here twice in 2 separate steps. And we saw this for the malonic ester synthesis in a previous video. So we can add leaving groups onto each of these. And what we're really going to do is take these 2 steps and just do them again. So we'll do them once for each, once for each alkyl halide. So this first step, we'll rip the alpha hydrogen off here, turn that alpha carbon into a nucleophile. You can do an SN2 reaction with one of these. I'll just do this first one, so bromoethane. And then, once you have the bromoethane attached, you can attach, you can attach the other alkyl group by doing the same sort of procedure again. Sodium methoxide and ethanol, that will rip the second alpha hydrogen off here, turn that into a nucleophile again, and then you can treat it with your second alkyl halide. And so, if this was our first one, use a different color for the second one. Purple here, that will be our second alkyl halide, so I'll draw that in. Sort of benzyl bromide. If you have a benzene ring and the benzylic carbon attached as a group, that's called a benzyl group, not to be confused with a phenyl group, which is just the benzene ring. So we sort of have benzyl bromide there, and we do an SN2 reaction with that, and then you do the hydrolysis and the decarboxylation with the acid and the heat, as we discussed in the mechanism in the previous video. And so overall, what you would do is, instead of just adding one R group, we would have added two. The first one is an ethyl group, so 1, 2, and the second one is a benzyl carbon and then the aromatic ring. And so both of those go on really the alpha carbon. That's this alpha carbon of ethyl acetoacetate. And they do that through two successive SN2 reactions. And so you'll notice that if you sort of go back to this original structure, that's what we have. We have the benzyl group and the ethyl group on that alpha carbon. So when you see a methyl ketone, you'd think in your mind, I can make that using the acetoacetic ester synthesis. Okay. Yet again, you would see a methyl ketone in C, and so you'd say to yourself, I can make that using the acetoacetic ester synthesis. And the features of that will always be the same, is you'll always start with ethyl acetoacetate. Then you'll always treat it with a strong base, sodium methoxide in ethanol solvent. That rips the alpha hydrogen off, turns that into a nucleophile that can do an SN2 reaction with an alkyl halide. And once you have that R group attached to that alpha carbon, then you can do hydrolysis. Then you can do hydrolysis. Then you can do hydrolysis with the acid and heat. So aqueous acid and heat. The acid will hydrolyze this ester, turn it into a carboxylic acid, and heat will decarboxylate it. So really what you end up adding in this procedure is the alpha carbon, the carbonyl carbon, and the methyl carbon of ethyl acetoacetate. So when you're trying to think about what alkyl halide you need to add, well, the alkyl halide you would take off the carbonyl and the two carbons on either side, because that comes from ethyl acetoacetate, not from the alkyl halide. So once you sort of have those organized in your mind, erase them. Those will come from ethyl acetoacetate. Notice that when you do that for this molecule, you end up with two separate carbon chains. And that's a sign that we're going to have to do these first two steps twice. And I think I might have neglected to do this in the previous one. Make sure you, of course, change those numbers. So this is 3, 4, 5. So going back up here, this should have been 3, 4, and 5. So each of these steps, this first step will turn this alpha carbon, rip the alpha hydrogen off of it, turn it into a nucleophile, and then you can do an SN2 reaction with your first alkyl halide. Now to get the alkyl halides, you just add a leaving group onto these two carbon chains that were left over. And so this will be one on the left. It's sort of a butyl group with a chlorine on it, or it could be any leaving group. So 4 carbons and a chlorine. And then, for the second one, you would have sort of isobutyl group and a chlorine, or a leaving group. And so those are your two alkyl halides. So as you do that reaction, you would end up adding two R groups on. One would be a butyl group, so 1, 2, 3, 4 carbons, and the other would be this isobutyl group. So 1 carbon and then a second that sort of branches into a snake's tongue. So this is that second group we added. Here's our first one, and you can see if you put the molecule together, that's the original molecule we had. We have those 4 carbons there, and the isobutyl group on the other side. So anytime you see a methyl ketone, a ketone with a methyl group on one side, you should think, I could make that using the acetoacetic ester synthesis. All right, let's try that same procedure for D. So in the acetoacetic ester synthesis, you always start with ethyl acetoacetate. The hydrogen here is the hydrogens there are very acidic because they're allylic to both of these pi bonds. So a base can easily rip them off and turn this carbon into a nucleophile. Then you can do an SN2 reaction with an alkyl halide. You'd attach a carbon onto here. You just have to get rid of this group. You do that by turning it into a carboxylic acid and then heating it up so it decarboxylates. So ultimately what you're doing is you're taking this alpha carbon, the carbonyl, and the methyl, and you're adding it onto whatever carbon you attached in the SN2 reaction. So when you're thinking backwards and you have a methyl ketone and you're thinking, what alkyl halide should I attach it to? You have to remove that 3-carbon group, the carbonyl and the 2 carbons on either side of it, because that's not coming from the alkyl halide, that's coming from ethyl acetoacetate in this acetoacetic ester synthesis. So you would identify that group, the carbonyl group and the carbons on either side, and once you have that, erase those. Those will come from ethyl acetoacetate. So when those are gone, you see that you have 2 carbon chains that are separated. That means that we're going to have to do these first 2 steps twice, once to put on each carbon chain. So we'll adjust the numbers here. 1, 2, then 3, 4, and 5. And we'll just put leaving groups onto each of these carbon chains where they connected, and that'll give us our 2 alkyl halides. So, and it doesn't matter which order you put them in, really. In this first one, I'll just use the methyl bromide, or the bromomethane. So that would be like this here. And for the second one, what we have is 4 carbons. So 1, 2, 3, 4, and then the bromine. So that's our second group there. And we just fill that into the otherwise standard recipe. So before each of those steps, we use the strong base to turn the alpha carbon into a nucleophile that will do an SN2 reaction with these alkyl halides. And at the very end, we treat it with aqueous acid, so hydronium. Turns this into a carboxylic acid in heat, which boils that carboxylic acid away, decarboxylates the molecule. So what we end up adding are these 2 carbon chains. So we have just the 1 methyl group from this first one on that alpha carbon, and then we have 4 carbons, 1, 2, 3, 4, also attached to the alpha carbon from ethyl acetoacetate. And so, if you sort of erase this and look back at our original molecule, you can see that that's exactly what we have. We have our methyl ketone group with the alpha carbon, and we've attached a methyl and a butyl group onto it. So in general, when you're doing this, when you're thinking about the acetoacetic ester synthesis from the perspective of a synthesis problem, you'd look for a methyl ketone. That's the key. That's the key word that would tell you or the key structure that would tell you do the acetoacetic ester synthesis. So then you'd write down the standard recipe. You always have ethyl acetoacetate, sodium methoxide and ethanol, and an alkyl halide, followed by acid, hydronium, and heat. You just have to figure out what the specific alkyl halides are. You do that by circling the ketone, the carbonyl and the two carbons on either side, and erasing it, and then just attaching a halogen to each of the pieces you have left. So hopefully this video gave you some practice thinking about the acetoacetic ester synthesis from the perspective of a synthesis, of a sort of retrosynthesis problem. They give us the products, and we had to figure out what reactants we needed in order to do these.